So my channel has a question on Argand diagrams, which are ways that we represent complex numbers which are different from ordinary numbers. And some background. Here's the question. And if we read it from a learned standpoint, we can see on the left that we have some locus, and we can see it's away from a particular point, and we're talking about the distance away from that point because of the modulus brackets is equal to some similar situation on the right, a set of locus points away from a certain point, and I know it's a distance because of that modulus bracket. So that's how you read it. And I'm going to keep those notes off to the side here just so we can see what I mean. So we look at this on the left-hand side here. We know that if we had a format that was z subtract z1, that our typical complex number, if we define it, is x1, because it has a real part, and a complex part, which is a certain number of I, like this. And so to know what that point is that we're away from, we want to be looking at what the z is subtracting in terms of its real and imaginary parts. And those real and imaginary parts give us the coordinate, which is the center point of our argument. It's the point at which we are focused on for our loci. So with that said, let's break it down. Over here we can make notes, and I encourage you to do so. We have our left-hand side first. That can be written as z subtract 6 plus 0, well, I times 0. So we'll say 0i. Essentially, there's no imaginary parts there. And if we look at our axes, this axis is no longer essentially what we're used to, the x-axis. We call it the real axis. And the y-axis, as we're used to, is actually in this setting called the imaginary axis. And it's an awful term, imaginary, because obviously we know it's rather a real thing in engineering that we must take into account these numbers. So we now have a way to plot these. We have a certain amount across the imaginary, or the real, which looks to me like the old y. And we have a certain amount across the x, which looks to me like this one. So we're talking about the loci, the sets of points which are a distance away from this xy coordinate, and it's the modulus that tells us it's a distance. Let's plot the 6, 0, and we'll see where that takes us. So roughly, what have we got over here for the 6 one? 2, so I'll do it here. So this is on the axis, essentially. We've got 6, 0. The scenario that you may have been given in, say, year 9, where you had to figure out a way to get past these sharks in the water. And you know if you get too close to one, it's going to detect you and get you. And so, how do you do it? What's the route to take? It's what we call the perpendicular bisector. Now, to be really technical, you may have drawn a straight line. That didn't work. Hold on. Yeah, there we go. You may have drawn a straight... that'll do. You may have drawn a straight line through it, and you may have taken your compass and set it to the distance of the other shark, like so. and then the other shark there, and the same on both sides. And then when you draw that down the center, you'll find that this is equidistant. It'd be the exact middle. And more than that, it will be perpendicular. So you can take this point here, and it is the same distance away as it is from that shark. And if you are in the middle, you're neither closer to one or the other, therefore you're the maximum away from both. And that's the same all the way down. Even though, okay, you're going to get a bit closer, you're still the very middle. The same principles are going to work here if we can read the locus all good. We've got one point here at 6, 0, and we're saying that the distance from those z, the set of dots that would make up the loci, the distance is equal to this. So the distance that it is away from that point that we've just defined is the same as the distance away from the point involved in the right-hand side. Let's quickly look at the right-hand side. We have z subtract 2 plus 0i. And we always take that negative out because the format has to be negative, because that's difference. This represents our x, this represents our y. So we're looking for the point 2, 0. Let's just put it on roughly. There's no need to do it 100% exact. But here's the point 2, 0. Now it's just like a shark. Those 2 points are the shark. And you're looking to say the distance from 6, 0 must be equal to the distance from 2, 0. And what are the sets of points which are equidistant from those two? It's the perpendicular bisector. Time to celebrate with a new color, red, crimson. The very center of 2, 6 is 4, 0. And so if we think about the perpendicular bisector, so this, as you can see, there's a point there which is equidistant, there's a point there which is equidistant. This line represents the point which is exactly equal to both dots. You can imagine if we went over here, we're much closer to the 6, 0. And likewise, if we went over here, we're much closer to the 2, 0. The only point where we're going to get satisfaction of our equality up there is this straight line here, the perpendicular bisector of those 2 points, which is defined as x equals 4 all the way up. And that is why the answer to the question in the multiple choice is x equals 4. Thank you for watching, and if you want another explanation, comment solution please.